What's up, guys? Haven't made a video like this in a while. And today I'm going to talk about convolutional neural networks, which is a building block, key building block of computer vision, which allows computers and artificial intelligence to classify images and detect features within images, like, for example, maybe detecting rust on a car or just detecting objects like for example, like Where's Waldo, where, there's this man with a striped shirt that's somewhere in an image and he's really hard to find. Um, so I'm just going to go ahead and explain kind of like how this stuff works. So you start off with an image, and the image is a bunch of numbers because it has pixel values. So it's actually just a matrix of image of pixel values that make up that image. And the computer will take a little grid, and a grid of numbers, and these numbers are randomly assigned. They're known as the weights. And the grid of weights will slide over the entire image, and it will multiply the pixel values times with the weight values to create another matrix or grid of numbers that is basically another version of the image. And then pooling takes place where another small grid goes over the image. And this time, rather than sliding like this one by one, it'll do like here, 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 here. So like it doesn't go, and basically does not cover the same area twice ever. And within the pooling, we'll take the largest individual number, the largest number from that grid, and take it and make a smaller grid that only has those largest values, which leads us to this guy right here. This process is a convolution. The neural network will have anywhere between 2 and 19 of these, maybe even more. I think I've even heard of them having as many as 50, depending on the exact circumstances and how much data you have, what you're trying to do with it, things like that. How big the images are may play a role. But at the end, what's going to happen is they'll keep getting, like, turning into these small boxes, smaller and smaller boxes, until you end up with your image has gone from an image here to a super long strand of pixel values. And then the flatten layer is applied, and if you do not have a flatten layer, the code will not work. It just won't. And then we're going to feed the results of these, those long strand of pixel values to a number of nodes that we set. And each node will have its own bias values. The weights of which are the values of these pixels are multiplied with the biases. And then we feed it to the final output layer, which the number of nodes here in the end is determined by how many different things we're classifying between. So say we're classifying between a car, truck, van, and a bike, we'd have 4 of these at the end. And, more or less, but another example, like totally different use case, is I heard of some guy that made a neural network like this that can classify or predict how popular an image is on Instagram. So I don't remember what the metric was, if it was like likes or engagement of some sort, but basically in that case you're going to have just one output node, because your output is a number rather than like a category. And the process is a little different. You use a different activation function, and it's not quite the same, but that's the gist of how this stuff works. And a little bit about the history. So this technology was created by Jan LeCun, who has been the head of AI at Facebook. He created this during his postdoc, and I think it was around the early 90s or late 80s. And it took until around 2012 for the technology to really get used, because that's when we finally started having enough data to do this. And that's when like the data explosion with everyone being on their phones and on the internet and on Instagram really or social media in general, really started taking off. And that's like really when this whole like AI and neural networks really started actually being practical, as opposed to just some like weird things some computer nerds would come up with. So here I've got some code that'll allow us to pretty much implement this technology of a convolutional neural network. So I'm not going to go too in depth on this code, but I'll leave it in the description. But basically, I've just made some things that'll make this process fast. So the first thing we have to do is create an instantiation. So the class called CNN right here, CNN, it is a bundle of functions, and the functions are just basically ways you can reuse your code, so that you write code and you can reuse that chunk of code over and over again as many times as you need to. So we're going to start our class, which is this right here. So this should work pretty well. And now we can tell it to do things, essentially. So the first thing we're going to do is we're going to create our data sets. And a lot of this has been done for us. The images have already been the converted into numbers. In the real world, you often have to download images and convert them to numbers. So now this function will allow us to turn these, basically create our data sets here. So we're using CIFAR images, which are 10 different categories of image, and it's often seen as a benchmark for measuring the performance of these computer vision tasks. Load data. So there we have. Oh, I see. I'm confusing myself here. Yeah. Okay, so there we have it. Should work. And now I'm going to show you what this looks like. So X. These are what the images actually look like. So I know it's very confusing, but these are all of the pixel values. So we have 3 channels of pixel values: red, blue, green. So yellow, for example, would have very high values for red and green, but very low to no values for blue. So that's just a way to paint how this looks. And now I'm going to explain what this means. So we have 50,000 images to train on. They are 32 by 32 pixels count, and there's 3 because there's 3 different color channels. So it's 3-dimensional. If it was a black and white image, it would only be 1-dimensional, or it'd be flat essentially. So the next step is we're going to build a model. And we'll build a classifier. So we have 10 different images, 10 different possible classes of image. So we're going to have 10, 32 because we're working with 32 by 32 image. 3 for the color channels. Kernel size, we're going to go with a 3. So basically just like this right here. This right here is a 3 by 3. Going to be a 3 by 3 grid. This will actually be a 2 by 2 grid. And we're going to have 3 of those convolutions I talked about. And then 2 for the pooling. So like it'll take like a 2 by 2 grid and take like of those 4 values, like that, whichever one has the highest value. And then activation, we're going to use ReLU. Typically best for these kinds of problems. Atom for optimizer. And if we were really serious, like in a real world situation, I would test between multiple. I'd actually test between multiple activation functions. And also dropout, we're going to use dropout. Basically, dropout will randomly shut off 50% of the nodes at any given time so that we never have to, the model basically won't get like too dependent on any part of the network. And accuracy, because that's our metric, usually is the metric. If we were like trying to diagnose a rare lung disease based on lung images, that would be another story because, if like only 1% of the people have the disease, and then if we go for accuracy, I mean, we could just say that no one has the disease and still have 99% accuracy, but being totally ineffective. So that's something you got to take into account when you're doing this. So we're going to build the model, and now we're going to train the model. So we're going to evaluate, train. So this way, we're going to train it on the X and Y because that's the images and the labels of the images. We're going to set epochs to 15 because I was playing around with it and 10 just didn't seem to be enough. And then we're going to set quiet to false. So this way it'll create a graph to show the model's performance and we can visualize it. So I'm going to say quiet is false, and now I believe that should work. So let me make sure that this is off to a what? I am missing that, aren't I? Okay, well, it's not good. Yeah, so I'm actually missing something. We're going to pass the model. So that way, the model needs to be in here. Otherwise, you can't train a model when you don't have the model. So it's working. This is going to take a while, so this video might be 2 parts, or I may just stop recording and restart recording. But so I'll show you the results when it's done. All right, so the training has been completed, and now we have this little graph showing how the model did. And to be honest, it didn't really do great. So these red and green lines. Actually, before I get into that, let me explain how this process works. So we took a set of 50,000 images, and the model was trained on 40,000 of those images, and then it evaluated itself by trying to label the other 10,000 without being trained on them. So like 40,000 images is like, this is a horse, this is a cat, this is an airplane. All right, now it's your turn. Now, like, you predict it, right? Kind of like the practice questions in a test, ACT practice questions. And then the other 10,000 is like it's taking the actual ACT test, It hasn't seen those questions before. And that's essentially what happens. And then that process is called an epoch. I set this process to take place 15 times. So there's 15 epochs, and by the end of it, for each epoch, we gradually got lower and lower loss and higher accuracy which is good. But the problem is it still didn't get that good, and uh, it was still only in the 60s and 70s for accuracy, which is not that's not a very good percentage. And also, there was a slight gap between how it did on the test training and how it did on the testing, which means it's indication of overfitting, which means it's memorizing more than it's actually learning. And this is part of why I put a dropout layer in there and used dropout I mentioned earlier. But even that wasn't really enough for this case. Now I'm going to show you the numbers behind it and an evaluation of how well the thing did. So I'm going to show you that real quick. So this will take a second. So yeah, 75% accuracy on the testing data, but when we trained it on this outside set of 10,000 images that had never been seen before by the computer, we only get 63.3% accuracy, which is not very good. And now I'm going to show you what these images actually look like. So let's take this image right here. So I'm sorry. Those are the pixel values of the image. This is the image. It is not very high resolution, but as you can see, it is a horse. And now let's see if the computer is able to recognize that that horse is a horse. So and as programmers, we start counting at 0. So this is actually the 8th image in the data set, not the 7th. Yeah. So as you can see, it predicts a number, which is 7. Now, that's not very helpful. But if we look over here, this is the guide. So basically, 1, 2, 3, 4, 5, 6, 7, 8, which basically it predicted that it is a horse. So this was actually correct. Now that was from the training set. Let's take one from the testing set and see how well that one does. So let's see what this will be the validation. So this is I believe it looks like a frog to me. And let's see if that gets predicted properly. Predicted a 6, so that is predicted as a frog. So this is correct as well. So it properly did it. So there you have it. So that is, so far from what we've done and what we've tested it on, it's good. But obviously that's a very, very tiny sample. But it's just kind of fun. Before I go real quick, I'll play around with it briefly, just like see what these images like are. Oh. What the heck am I doing? Okay, I was hitting Control instead of Shift. So what we got here is I can't even say with, oh, that's like a deer. That's a deer. This is a, to be honest, I won't even blame the computer if it doesn't, not able to classify that. Let's see what the computer says it is. The computer says that is a 4, which is a deer. So it says that's a deer. I'm going to take its word for it. So yeah, that is like pretty much that in a nutshell. And this is how you can train a computer to classify images, and you can find any kind of collection of images you want, and it will at least do a somewhat decent job at doing this, at doing it. And that is all for this video.